Okay, so we talked about the need of doing quantitative analysis, and we look at the execution time, which is central to the embedded system design. Then we're gonna look at in the next few slides how we address this problem of finding the worst case execution time. We're going to start by looking at the programs, the software programs, as graphs. This will give us a powerful tool to start some analysis. And let's delve into that. Okay, so this is a example program. It's a modular explanation. This is part of the encryption algorithms that are used by this part of the encryption algorithm. What we're doing here is we're trying to do this modular exponentiation calculation, and the input to this function. Let's start from the first line. We define the exponent bits as 32. The reason we have 32 is because we store the exponent, that number, as a 32-bit integer. In fact, all these three arguments to this function are unsigned integers. So all of them are 32-bit. And that's the reason we have this constant number exp bits is a 32. And this function is modular exponentiation. The input arguments are all unsigned integer. The return value is also unsigned integer type. We have base, exponent, and modular. In the function, we declare integer I as the loop iteration variable, and we initialize the result as 1 because we're going to do a lot of multiplication. In the line 9, we initialize the loop iteration variable I as 32 because we're going to go through every single bit of the exponent, this value, and we're going to do the following loop. Within line 10, it's to say that the number of iterations will depend on will depend on whether I is greater than 0 or not. And because I was initialized as 32, a constant number, so we know we're gonna expecting the loop iteration variable I to decrement. Otherwise, you're going to be having a infinite loop. And if you look at line 16, it's I minus minus, so we're going to decrement by 1 every time. So we can expect that this while loop it'll repeat for 32 times. So from line 11 to line 16, all these lines will be repeated for 32 times. And line 11 is a if statement. So it's going to be a branch. What we're checking here is to see if the current exponent is a even number or odd number. If it is an even number, that will make this condition true. And in that case, we're going to multiply the result with the base and then do the modular and update the result. Otherwise, we don't do that. Then the next thing we do is to right shift the exponent. So basically, we're going to be reducing the exponent by 2 every time. And then line 15 is to do a square on the base and then do the modular and update the base. Okay. And line 16 is to decrement the loop iteration variable and then go back to line 10 for the next iteration. and eventually line 18 will return the result. Okay, so it's a very simple program. You don't have to you don't have to know too much about the encryption algorithm, but we're just looking at this simple modular explanation function to see how some algorithms are implemented in C. The exact formulation of this calculation is defined here. Okay, so given that C code, what we want to do here is to represent or analyze this piece of code. And we are doing a few things here. First of all, so all the lines of code within this function are captured here in this diagram. And we're separating them, actually grouping some of the statements, some of the lines, and into so-called basic block. So if you look at the first box here, result equal to 1, I assign initialize as EXP bits, so that's 32. We define a basic block as a sequence of series instructions. They going to be executed all together without exception, and they only have one entry point and have one exit point. So if you let's go back to the previous one. So this is what we start with. We start with line 7 to the very end. So we know these two lines, although there's a space between them, but these two statements, these two lines are going to be executed together. So this is going to be first executed than this one. And then if we look further, this while this line will be executed, between line 10, line 11, depends on the value of I, we may or may not execute line 11. So that's the reason we don't put line 10 and 11 into one single box as we do on line 7 and 9. So 7 and 9 are considered in one basic block, whereas 10 and 11, these two lines are considered separate in separate blocks, separate basic blocks. Again, we define basic blocks as a sequence of instructions that will be executed together, meaning not the same time, not necessarily the same time, but either both of them be executed or none of them be executed. And when we have this basic block, we can know that, we can be sure that there's one entry point to this basic block, there's one exit from this basic block. And then the while loop becomes here, this block, which is to check whether I is greater than 0 or not. We use 0 on the outgoing line to indicate the condition is false. So if I is not greater than 0, it will jump to here to return the result. Otherwise, when we exit, we have a 1 marked on the exiting edge or exiting line to indicate this is the path will be taken if this condition is true. So the next basic block is this exponent and 1 equals to 1. So this is another condition. This is the if statement, which will check this condition. If that's true, then this line of code is going to be executed. No matter what, the next basic block will be these 3 lines exponent right shift, base to the square and to the modular, and then decrement I. And these three lines of code are put into one basic block because there's no branches among them. All these three lines will be executed together. Does this make sense? Any questions?
No questions.
Okay. Okay, so we'll see shortly why we're doing this. But so far, what we're doing is to come up with a control flow graph to understand the program itself just by looking at the statements line by line. There are software tools to help you do this, but eventually you will have so-called a graph, control flow graph, that will use these basic blocks and this ingress and egress lines to indicate the execution path of this program. And you can see there are a lot of different possibilities how this program will be executed. If you go into this one here, because I initially is 32, so you will find that you will always execute this path. But depends on the input value of this exponent, you may or may not execute this line. Well, actually you do execute this line, but the output will be, the next line will be depend on the actual value of the exponent. So you may execute this basic block or just skip that to this, jump to this next basic block. See, there's a question. Okay, so the meaning of this right shift, well, this double right greater sign equal to 1, that means we're going to right shift this value by 1 every time. So if you have less than sign, and then that will be shifting the value to the left for 1 bit.
So does it mean multiplying by 2 or dividing by 2?
So this is divided by 2.
Oh, okay.
Yeah. So if,
thank you.
Yeah, if you have 4 initially and then right shift for 1 bit, then becomes 2.
Oh, okay.
Okay, so we have this control flow graph, and we can use this control flow graph to do very interesting analysis. We want to use this program path, i.e. the control flow graph, to find the longest path through the program. Also, we would like to find the loop bounds. In our previous example, the loop bound is 32, so we know that by the value of the constant 32, and you decrement 1 at a time, so you will have 32 loops, 32 loop iterations. Also, use this control flow graph, we can identify feasible paths through the program. We can identify dependencies among different code segments. The second part of it is that because we have these basic blocks, we can generate bounds on runtime on the platform. What we mean here is these small blocks, we call it basic blocks, they are sequences of instructions. If we can measure the execution time of these small code segments, these basic blocks, then we can use the information to, together with the control flow graph, to understand the overall execution time. But we have to say that to understand the execution time or to get the bounds execution on upper bound of these basic blocks, we need to know the actual process architecture. We need to understand the cache behavior, pipeline stalls, branch predictions, because all these factors will affect the actual execution time of the basic blocks. But we'll talk about that later. And with these two aspects or two angles, we have program path analysis, we have processor behavior analysis. We can use the outputs from both analysis, feed them to each other, and to generate an overall understanding of this program. Now, before we do anything, let's look at this interesting example. This is where we can possibly use program path analysis. So we have a few lines of code, and we have nested for loops. We have a outer for loop for 100 iterations, and inner for loop for 100 iterations. Okay, so within the inner for loop, we have these several lines of code. So we know this several lines of code will be executed by 100 times 100. That's 10,000 times. It's just because of these two nested for loops. And within the for loop, we have an if statement. And it depends on the value of this array, this particular element. If it is greater than or equal to 0, we will put that into a positive total and then positive count. And if that number is a negative number, then we're going to accumulate that to the negative total and also increment the negative counter. Okay, this is kind of a toy example, but the point here is you will possibly have these branch instructions which will give you two possible paths. So for each loop iteration, you may execute this path or this path. Or if we think about this as a basic block, that means we can either execute this basic block or this basic block, not both. So if we think further, because we know the number of iterations, so what will be the number of possible paths? How do we calculate that?
Is it 20,000?
Okay, that's a good guess. So here we're not really talking about just one-time execution. If you have a input data, let's say you have an array full of data integers, then that will give you one, that will deterministically tell you whether you go this way or this way. But the problem is we are doing this analysis without knowing ahead of time what are the values in the array. And you can run this program for many times. Depends on the array data, you may end up taking this path or this path. So if you have different inputs for the array, for one execution, this first execution may take a different path compared to the second time you execute this whole segment. And if we consider these separate paths, the question really is how many different paths that are possible. So let me make this problem even simpler. So let's say if we don't have this for loop at all, we only have this from the if up to here. Then given different inputs, how many possible paths, how many different paths that we can possibly have?
2.
Exactly, that'll be 2. So either this path or this path, right? Either positive or negative. But that's the case, we don't have these for loops. If we have a for loop that gives you, let's say, a loop duration up to 2, so let's say we want to execute this if statement for twice, then how many paths that we're going to have? So that'll be 2 times 2, because you're going to be executing this if for 2 times, and depends on the input, you may end up having positive, or positive, negative, or positive, or negative, positive, or negative, negative. So when you have 10,000 loop iterations, you are looking at a very large number of different paths that are possible. For a given array with numbers, you will end up executing, going through this whole program on a particular path. But now we're doing this analysis, trying to find out what is the worst case executing time. So we don't know of beforehand what will be the input values for the array. So that's why every loop iteration, you have 2 possibilities. Now you have 10,000 iterations, then you're going to have 2 to the power of 10,000 these many different paths. So that means this, worst case analysis using this, to exhaust, do an exhaustive search, that's not feasible. Now, this example that we saw earlier, this is the modular exponentiation function. We saw the same code before. And in this case, we have a while loop. The condition is I is greater than 0. Can we determine the loop bounds? Well, in other words, do we know exactly how many times this loop is going to be executed?
Uh, 32 times?
Yes, so 32 times, as we explained before. I is initialized at 32, and I is decremented by 1 in every loop iteration, so that gives you 32 times. If you decrement I by 2 every iteration, then that will give you 16 times. So with these kind of structure, it's possible to infer the number of times a loop is going to be executed. So which will make your analysis possible. But some other cases, you might not be able to figure out exactly the number of times. For example, if I is one of the arguments here as the input, and depends on the input value, this I will determine your number of loop iterations.